This is a puzzle pyramid. It weighs about 200 grams. I know it because I weighed it on a weighing scale. But what if I want to measure something that's much larger than this? What if I want to measure the weight of Earth itself? Okay, so not only what I wish to do is impossible, I cannot weigh Earth on a weighing scale, but what I should be finding rather is the mass of planet Earth, not its weight. We are so used to using mass and weight synonymously in our daily life now that we have completely forgotten the difference between them. Now, how are the weight and masses different from each other? Well, mass is an intrinsic property of a material or an object based on the amount of matter it is composed of. But weight, even though we are used to using weight in terms of kilograms or pounds in various parts of the world, weight is actually a force in physics. And the SI units of weight is kilogram, meter, second square. So what do we measure when we say that we are measuring weight? The Earth has its own gravity. Now that gravity is actually a gravitational acceleration and it's approximated to the value of 9.82 meters per second square. Now when an object is close by or near to the surface of Earth, that gravitational acceleration actually acts on an object. For example, if I am an infalling matter towards Earth, then the gravitational acceleration of Earth is impacted on me, and mass of my body and the gravitational acceleration that the Earth imparts on me together combines and forms my weight. So if I am, for example, now landed on Moon, my weight would significantly reduce because the gravitational acceleration of Moon is 1.62 meters per second square, but my mass on Moon remains the same. So according to the Newton's second law of motion, which is very simple, it's force is equal to mass times acceleration. Here the force is weight, the mass is of course any object or a body, in this case me if I go and land on Moon, which remains the same whatsoever. Even if I am in space drifting away in lonely isolated space, my mass remains the same until I lose the matter from within my body itself. Mass is volume of the matter I am made up of times its density, and the smaller case g that we refer to is a gravitational acceleration. So as much as the smaller g varies from one place to another, your weight actually changes. On the Moon, it's the same thing, that the gravitational acceleration is different now. So now if I am on Moon and on Earth my weight was say 60 kilograms, on Moon my weight would be as low as 9.96 kilograms. So it is even less than 1/6 what my weight was when I was on Earth. And that's only because of the change in the gravitational acceleration. Just for fun, I have provided some links below in the description where you can check your weight on various planets in the solar system and on satellites like Moon. So back to measuring Earth's mass, not its weight, its mass. There have been several different ways of measuring Earth's mass, but I'm going to take one interesting approach. You might have heard of a famous German astronomer by the name of Johannes Kepler. He described the motion of planets around the Sun into 3 laws, and we are interested in his third law. But before we go to the Kepler's third law of motion, let's first discuss some very small basics. We know that the Moon actually revolves around the Earth. The Moon's revolution is basically an ellipse. It makes an elliptical orbit. When it completes one orbit, it's an ellipse. The longest segment that we can draw within an ellipse, from one part of ellipse to the other part of it, it's called the diameter or the major axis in ellipse, and half of that is called the semi-major axis. So the Kepler's third law of motion states that the square of the time that it took the Moon to orbit the Earth once is directly proportional to the cube of the semi-major axis of the orbit. The semi-major axis is about 384,400,000 meters, and the time it takes for Moon to complete one orbit around Earth is about 27.32 days, which is approximately 2,361,000 seconds. So assuming that the time it takes for Moon to complete one orbit around the Earth is t, and the semi-major axis is a, t square is directly proportional to a cube according to the Kepler's third law of motion. The constant of proportionality over here is a 4 pi square divided by uppercase g multiplied by uppercase m. Now the m over here is of course the mass of Earth, which we want to determine, but the big G over here, it's a gravitational constant. It's an experimental value, so it changes a bit from time to time, but it's a physical constant similar to the speed of light. So now you can see the values of the orbital time t, the semi-major axis a, and also g, which is 6.673 times 10 raised to minus 11 meter cube per kilogram per second square. So now, after rearranging the equation and keeping the mass of the earth on the left hand side and the rest of the equation on the right hand side, we find the approximate value of the mass is 6 times 10 raised to 24 kilograms, which is also called as 6,000 yottagrams. So the value of the mass of the earth actually estimated by NASA themselves is quite close. It's 5.97 times 10 raised to 24 kilograms. Now, a little bit variations can occur actually because of some of the approximations that we take. If you think that the mass of the earth is actually quite large and the earth is very, very massive, the sun, which is at the center of our solar system, can contain the mass of 333,000 Earths in itself. And the worst part is that the sun is not even the brightest or the most massive star in our own Milky Way galaxy. And there are more than 200 billion such stars or even massive stars in our own galaxy. So just imagine the tiny, tiny speck that we are in the universe. Now, thinking about the mass of the sun and the mass of the earth, let me come to the point as to who was the most heaviest human to have ever lived on earth. He was a US citizen by the name of John Brower Minnock, and his weight was an astounding 635 kilograms or 1400 pounds, or you can call 100 stones. Now that's a heavy person. Unfortunately, he died because of a disease at an age of around 40. He was born in 1941 and he died in somewhere 1983. Now, after measuring the mass of Earth and also knowing the heaviest human ever to have lived on Earth, my mind actually seeks as to what could be the most subtle thing or matter which was ever weighed. Let's see, one of the lightest metal to ever have been developed is called microlattice metal. It's actually a 3D lattice and it is 99.99% pure air, and its walls has a thickness of about 100 nanometers, which is 1000 times smaller than a human hair. Now that's really light. Now many religions in the world like Hinduism, Jainism, Buddhism believe the existence of soul, that when a human body dies, the soul leaves its body. Now, based on this hypothesis or this belief, a physician by the name of Dr. McDougall in early 1900s actually took it on himself to try to measure the weight of a soul. In his experiment, he had 6 patients suffering from tuberculosis and were diagnosed to die very soon. When he saw that the death was just few hours away, he put their beds on the industrialized weighing scales, which were sensitive to about 5.5 grams or 2/10 of an ounce. When the soul departed the body, according to his hypothesis, or during the time of the death, the body lost the weight of 21 grams. So he reported in his hypothesis or in his thesis or in his study that the weight of the soul is 21 grams. He tried to perform the same experiment on few dogs, but when they died, there was no change in their weight. So he concluded that the dogs do not have a soul. Now, this study was about to be published in 1907 by him in 1 or 2 of the US journals, but before he could actually publish, the New York Times actually just broke out with an article about it. He did eventually publish in that year in the journals. Now, was that the most mind-boggling experiment ever heard, or what? I wish that we as humans, as the people of science, should be as bold as Dr. McDougall. The point is, I don't support his experiment or his hypothesis completely or his results, but what I do support is his boldness to try to face, to try to see, or to try to seek whether there is any truth into what has been told, or whether do we have enough of the establishment or the materials to actually even measure the truth in something or not. And as always, thanks for watching and see you again with a new thought. This is Jim signing off.